それではそろそろお時間になりますので、OpenPOWER の最後のセッションになりますが、NVIDIA サンタクララから参りましたジョン・アシュレイによる、OpenPOWER のアプリケーションと、OpenPOWER のプラットフォームへのポーティングを中心としたお話をさせていただきたいと思います。はい、ジョン、スタート。
Thank you. As you have been told, and some of you may have seen me talk earlier, you'll see some of the same slides. I won't spend very much time on those, just enough for those that weren't here. I'm going to talk about three things today in this talk. One, I'm going to give you a quick overview of what the OpenPOWER Foundation is and why it exists and what NVIDIA is doing in it. I'm going to spend most of my time talking about the software ecosystem and the process that we and IBM at least are going through on porting some of the high-value scientific codes. And then I'm going to also cover at the end some of the resources that are available if you want to find hardware, compilers, tools, infrastructure, advice on moving software over to support OpenPOWER either exclusively or as well as other platforms. So OpenPOWER is really about being an environment where multiple companies can innovate on their technology. So we can all do what we're best at, we can make it better, and we can do it in a place where we can cooperate with other companies, some of whom we compete with anyway in other areas, but at least in an infrastructure sense, we can interoperate. That means that customers can build systems with the most hopefully innovative and suitable parts instead of having to go to sort of a one-size-fits-all environment. So a foundational element of that is the power processor itself. It's an established industrial strength, well understood, and perhaps most important for most of us in the consortium, a very strong manager of data. It's got high memory bandwidth, it always has. It's always done a good job managing a lot of I/O. In this modern day of data challenges, it's a great foundation to sit at the center of this ecosystem that we're all innovating around. So when the OpenPOWER Foundation started, there were 5 companies that were members. There were 5 founders. We had one customer in the software layer. We had IBM playing at several layers. NVIDIA was the only accelerator firm. Tyan came in as a system vendor. So already at the beginning, we knew that IBM was not going to be the only place you could buy a power server or an OpenPOWER server from. You're going to be able to get them from Tyan too. And that was December 2013 when we announced this effort. And we started telling our story about this is a place where you can come and you can innovate. You can do creative things, you can improve your products, and you can interoperate without sort of the constraints of a one-size-fits-all unified monolithic model. And it's worked pretty well. We now have over 145 members in the consortium. One of the things that is perhaps really interesting is we have multiple members at every layer. So Sugon Power Core is going to make power chips, right? You won't even have to go to IBM to get your power server chip if you don't want to. You don't have to go to just one vendor to get your boards or your systems. What that means is you're going to get a variety of motherboard options and a variety of system options and configurations. Some of those will include NVIDIA hardware and some won't. And we're okay with that, right? Because the ecosystem gets bigger and more innovative the more inclusive we become. Another thing that's really interesting to see is this layer up here. Implementation, HPC, research. These are customers. These are people who are thinking forward, right? So as a vendor, we have a tendency to look at the things we can solve today and in the near term because that's where we can sell product. But these people are, in addition to looking at those problems, they're also looking further out, and they're bringing that drive and that focus on, hey, I know you want to look at this problem, but we also want you to think about these problems, to the whole consortium. So that's coming up and down this whole stack. So NVIDIA is really happy to be part of the OpenPOWER Foundation. And I'm going to move into the software ecosystem a little bit now. One of the key things about OpenPOWER is it is based on Linux. By being based on Linux and by porting little endian Linux, so standard Linux, over to Power, all the data that you use in your traditional Intel-based systems is compatible. All the system tools you sort of expect to have there pretty much are there. All the programming languages, all the scripting languages, all the virtualization tools are basically there. The operating systems you want, the flavors of Linux you want, all there. There's about 1,600, a little over 1,600, I think, vendors and organizations that are moving software to or have succeeded already in moving all their software over. They play in spaces like the cloud, they play in spaces like data management, they play in mobile, they play in Internet of Things, right? Really across the board. And again, that's partly because of adopting that standard open Linux. If it works on Linux today, it generally works on OpenPOWER. I talked about big data just a second ago. One of the recognitions of that, right? These platforms are good for data. A lot of us are innovating around moving data more quickly, managing data more robustly, more energy efficiently. And so a recognition of that is this joint big data center being set up in the UK. If you've been in other sessions here, you will have seen the slides like this one at least twice now. There's a firm called GPUDB that's a third party. They're an independent software provider. They do a lot of work with the US federal government. And they've done testing with the current generation of OpenPOWER systems, and they're already faster. But what they see as exciting is that roadmap for OpenPOWER includes from NVIDIA and IBM NVLink, which is a technology that lets the GPU and the CPU communicate faster. And when that becomes available commercially, they figure they will scale up linearly with every performance improvement we give them in that link. Their programs will just run faster. It's that simple. They literally get back to a Moore's Law place, which is happy because obviously you don't get that in the rest of the software world anymore. The Coral projects, these big DOE supercomputers have been talked about already several times, but if you haven't been in any of those sessions, the power roadmap has been validated. The products are being bought. The roadmap has been bought. There are delivery commitments, right? We and IBM and Mellanox are delivering 2 leadership class supercomputers to the Department of Energy in 2017 based on the technologies and the software stacks and the ecosystem coming out of OpenPOWER. I'm not going to talk through the details of the various kinds of apps that the Coral system is looking at. What I want to focus on is sort of the fact that they're really looking at high-value scientific apps, right? Applications that are doing leadership class science. And I'm going to talk about the process of porting those over and sort of the status of those. I'm going to talk about that subset of things for 2 reasons. One, it's a fairly important subset of things. And 2, third-party commercial software firms are very picky about when they announce whether they've ported or not, what they want to say about it. And at least in aggregate, I can talk about the software things in a public forum much more easily if I talk about the scientific applications. So when we look at the process of porting a application to Power plus GPU, and I'm going to primarily focus on Power plus GPU because I'm from NVIDIA. There's a similar process that gets followed when you're just porting something to Power, and I'll give you some numbers on that at the end. The first thing we do is we profile the existing code, right? Generally, if we're porting it, that means it must exist somewhere else already. Let's understand how it runs there. So that's step one. Understand where it runs and what the bottlenecks are at the problem sizes of interest in the current existing implementation. And then we try and build it on Power. And this is where we discover the explicit dependencies on either Intel or usually just Intel, sometimes Intel and ARM. So explicit dependencies are things like inline assembly code, which obviously you have to then go and add a non-assembly path for, or a new assembly path for. And build dependencies. So things in the make file that check the environment and go, oh, you're on Power, I don't build here, and stop. Or they assume that if you're on Power, you must be big endian, and they run a different path through the build, and you really want them to be little endian now, and they just aren't ready for that. And so the second explicit area of dependencies tend to live in the make file, or CMake, or whatever your build system is. But once you've flushed those things out, which is not technically terribly hard, but it can be tedious sometimes, now you can finally profile the new code. And when you do that, you start to find the implicit dependencies on Intel architecture. A lot of these codes have been around for 10, 20, sometimes more years. And when decisions have been made about how to do something, almost always the option that runs fastest on Intel is the option that was chosen. And it's not just that ran fastest on x86, it's that ran fastest on x86 when the decision was made, which if that decision was made 15 years ago, is optimized for a very different environment than the highly parallel, highly data capable environment that the code's in on Power. So we've got the profile, we start looking at where it's faster, where it's slower, and we start trying to find these implicit dependencies, and now we start that tuning loop. We tune, we profile. We can go around this loop several times. We can also start taking advantage of the fact that these systems are slightly different in their performance characteristics, in the number of threads they support, in the cache sizes per core, and so you can start doing work with those things as well. And at some point, you go around this loop and you get a profile of the code, and you finally decide, yeah, I must be done now. This code is now ported, I'm going to call it done. And I will talk about how we make that decision because it's different today than it will be tomorrow. So currently of these, we jointly with IBM maintain a list of sort of high-value scientific codes, gets added to by the various research groups and the people going out to bid for projects. And we have 66 codes that are Power plus, or that we're targeting for Power plus GPU. Of those, we have 26 of them currently in this loop. Now, I gave a very similar talk to this in Taiwan 3 weeks ago. When I did that, this number was 30, and this number was 20-some, I think. So the loop is going fast, and it's and the total is growing. And 40 of the codes we consider done for now. They are ported. That doesn't mean you couldn't get more performance out of them, but it means, because you could always tune them more, but it means they're done. And if you just wanted to know the numbers for Power, if it will advance, right now there's 113 that are considered ported and 58 that are still in process. And I mentioned, right, done is sort of subjective, and it differs today from tomorrow. So going back to what is done. Today, the innovation engine is only starting in OpenPOWER. A lot of the technologies we have to build things out of are the same technologies we have today. PCIe bus for interconnect. We have the same GPUs in the server. We have the same networking capability integrated to the CPU over the PCIe bus. And so today, if we look at the profile of an application, and it is bottlenecked on the GPU, on the ultra parallel bit of code, it doesn't matter if it's computation and math bound, if it's memory bandwidth bound, or if it's bound by the data transfer rate to the CPU, performance should be roughly the same because it's the same GPU on both sides today. So if performance is roughly equivalent between Power and GPU and x86 and GPU, we're done. That's all we expect today. If the limiter is on the CPU side, if it's in the serial section of the code, and it's math limited, it's some flop limit, some arithmetic limit, then we expect the performance to be similar, maybe a little less, maybe a little more, but very close to the same as today. And when we get there, we're done. If, however, we are memory bandwidth bound or I/O bound in the I/O subsystem and not in the CPU and not in the I/O subsystem, if we're really memory bound, we expect to be quite a bit faster. And we expect that because raw memory bandwidth on the power chips is a factor of 2 or more better per socket, depending on the configuration. And so if that's the limiting factor for performance, it had better be faster. And if it's not, we need to do more work. There are implicit dependencies somewhere that are keeping us from using that bandwidth. And again, if the problem is really scaling outside of a node, if it's communications over Ethernet or InfiniBand, today it can't be faster. When we're equivalent, we're done. So that's the situation today. But I mentioned we have this innovation roadmap. We have this committed roadmap. We have systems we're delivering to customers that have improvements in things like NVLink, which gives us a faster communication between the GPU and the CPU. We have improvements in things like CAPI attached InfiniBand. We have improvements throughout the architecture coming. And so when we have those improvements, done changes. So again, if we're bound in the GPUs, then relative to the new generation of GPU on alternative architectures, either ARM or x86, we would expect to be at least as fast if we are math or memory bound. And I say at least as fast because one of the things that sometimes holds you back is you just can't feed the engines fast enough from the CPU's main memory if the problem is big enough. And so if the limiting factor is communications between the CPU and the GPU, and NVLink, even in its first version, is 3 to 5 times faster than PCIe, then we had better be 3 to 5 times faster, or we're not done tuning yet. And that also flows back into here. Because we can now feed the GPU faster, we had better be able to take advantage of that. If the limit is on the CPU side, if it's on the serial side of the computation, and we are memory bandwidth bound, well, we still expect the CPU socket in Power to have more bandwidth than either an ARM or an x86 server by a substantial margin, and so we had better be faster still. But we also should have faster I/O, because now we have potentially not only this enhanced, the next generations of InfiniBand, but we potentially have CAPI attached InfiniBand. So it has the ability to move certain messages with lower latency, with higher bandwidth, et cetera, through the system. Right? It may not be higher bandwidth over the wire, but it's higher bandwidth and better latency through the system. So we expect it to be faster here. And the interesting thing is, even if the program is limited on the CPU socket's use of flops. And even if the next generation of Intel or ARM chips doubles or whatever ratio they improve their flop performance by, we expect to be at least as fast on that code, even if it's serially bound. And the reason for that is we now have NVLink. We can offload computation more cheaply to the GPU than we could before. It costs us 2 to 3 times less to offload a computation. And if we are math bound, not bandwidth bound on the CPU, then that computation should be ripe for offloading, and we should be able to move at least some of the critical bits over to the GPU, which has a huge advantage on the math side relative to a CPU socket. And the overall code should be at least as fast, if not faster, even if its performance limiter is the CPU's math performance. This is sort of the way we're thinking about things, right? Even if the GPUs are identical, when NVLink is there, it costs us less to do the offload. We can afford to push more work to the GPU. The GPU can do it faster. Our next generation GPU has 4 times the memory bandwidth than our current generation. So we get huge benefits in this column on these big data problems relative to where we are today. And because of NVLink, we get it on get to use that advantage more effectively on Power than on any other platform. And that's part of why we're so excited about being in a place where we can innovate that way. And we also get the benefit going out of the box to other boxes. We didn't have to build a faster InfiniBand network. Mellanox and IBM took care of that piece for us. Now we can communicate to a GPU and another server more quickly. So we get the benefits of all that innovation as well. And we're actually seeing results that track to these expectations, and we are using similar processes and thinking internally and with customers and validating these expectations at sort of finer and higher levels of detail going forward. So that kind of is what I wanted to talk about the process. And obviously in terms of tools and resources, I want to touch on that as well. I really do want to make sure that we leave a little bit of time here, but IBM is all in on OpenPOWER. IBM has global resources available to help you move code or to help you figure out how to integrate your products into OpenPOWER. So they have IBM Innovation Centers, they have ecosystem centers, they have various vertical software lines of business that you can interface with. They have development clouds. They have established porting centers around the world. So there's almost certain to be one near your software developers, because obviously even if your company is here, you may have development globally too. There's likely to be one near your key developers. If you are a university, a research group, a small company that maybe is wondering, we don't want to interface with IBM that way. We want to sort of do our own thing. We want to be a little further out. There are a lot of options in the cloud spread out through the world. And one of the most interesting ones, to my mind, is SuperVessel in China. They're up and running now. And they are, I think right now, the academic research and university line is up. The individual developer stuff is coming up, and Enterprise Zone is following soon. And you can go to this link if you wanted, or to the PT OpenPOWER link on the previous slide, and get more information about that. And you could spin up your own virtual instance on Power in the cloud to look at what it's going to take to port your software, how your software is going to perform, what explicit or implicit dependencies you have now, so that when that innovation roadmap kicks in and starts delivering systems that can do things no other system can do, you already know what it's going to take you to take advantage of that. You're already ready to pick up and join that train. Are there any questions? If not, this deck should be available afterwards. I'm not quite sure how you'll get to it, but it will be made available, or you can always email me.
何かご質問のある方いらっしゃいますでしょうか。オープンパワー最後のセッションとなりますので、何か、全般的なことでも構いませんが、何かご質問があればお受けしたいと思いますが、いかがでしょうか。よろしいでしょうかね。はい、では本日はありがとうございました。Thank you, John.